Okay, welcome everyone to the Oxford seminar. This week we'll be hearing from Ray A. Pedersen, who'll be talking about Everettian quantum mechanics and the problem of ontological extravagance.
Great, thank you. So this is I should state up front that this is a work in progress. It's the motivating chapter for my full dissertation. And we're going to be talking a bit about values in science with theory choice and extra empirical considerations. But I thought it might be helpful to have a bit of a pre-introduction to the normal introduction to this talk. So you might wonder, what's Everettian quantum mechanics and how is it meaningfully different from ordinary quantum mechanics or orthodox quantum mechanics, or the Copenhagen interpretation? So I'll tell a very short, or I guess I have quite a bit of time, so maybe I'll give you an embellished origin story. So Niels Bohr, pictured here on the left, was a visitor in residence at Princeton in the 1950s. During which time Hugh Everett on the right was a PhD student. And Everett started his PhD working on game theory, but as he met Bohr and took long walks with him and his assistant, Pedersen, Everett became very, very interested in the foundations of quantum mechanics and in particular the measurement problem. So he basically proposed a whole new formalism for quantum mechanics that solves the measurement problem. But there was some drama to this. As you can imagine, Bohr is the father of ordinary quantum mechanics and this principle called complementarity, and he did not take kindly to being challenged by this kid, Everett. And essentially, he and his inner circle from Copenhagen wound up driving Everett out of academia. There's some historical evidence that suggests that Everett was mostly interested in money anyway, so he wasn't going to stick around academia. But in any case, had he wanted to pursue a career, sort of like his advisor, John Wheeler, wanted him to, there was no path forward unless he bowed down to Bohr. So following the initial proposal of the theory, there was relative silence on it until it started getting picked up in the 1970s, and it was discussed at a few conferences, and then work really picked up in the 90s. So there was this huge gap, and actually historically some folks working in Oxford really helped bring it back to life. So that's the conceptual or the historical introduction. Now on to some technicalities. I have sort of a very non-technical introduction and then I go a little more technical. So as for the non-technical, ordinary orthodox quantum mechanics involves the deterministic evolution of the wave function psi plus a stochastic collapse principle. Everettian quantum mechanics, or alternatively, the deterministic evolution of psi plus a hidden variable to uniquely select out a value. EQM just demands the deterministic evolution of this wave function. So you can see it's quite a bit simpler. So what does this look like? We have the wave function that essentially, at the very least, it describes the probability of particular outcomes after an experiment or observation or what have you. So on the sort of orthodox versions of quantum mechanics, we see how there's this nice deterministic evolution and then either stochastic collapse happens, which I don't really know what the mechanism for that is supposed to be. That's sort of the measurement problem. Or we have a hidden variable that picks out the unique value. In any case, we have two different processes at work, and there's something mysterious going on. EQM, on the other hand, does away with all of that and says, we just have the unitary evolution of the wave function. Okay, so then you might wonder, how do we seem to see unique outcomes of processes. So I'll show how this works with a simpler case, which we call the Stern-Gerlach experiment. Is anyone familiar with this from? Yeah, okay, cool, yeah. So I won't take too much time here then. Basically, we send a particle through an inhomogeneous magnetic field, and depending on how the particle interacts with this detector, which is represented with this nice line. Either we say that particle has the property of being spin up or spin down. If you run this experiment over very many trials, you'll see if you prepare the particle in a particular way, approximately half of the particles will come up as spin up and half will come up as spin down. Cool. So for each electron, we begin in the superposition of states, and then we wind up via some process in an eigenstate. Okay, so with these other versions of quantum mechanics, this is sort of what the world looks like before and after measurement, where measurement takes place at T sub m. Everettian quantum mechanics looks a bit more like this. So via a decoherence process, these two elements of the superposition become entangled with your detector. So the detector itself enters a state of superposition along with the world, and we see this branching of the world. So where there once was one world, there now are two. Okay. So EQM gives rise to a structure that looks a bit like this. It's quite a bit more complicated if we're looking at processes that have more than two outcomes. And orthodox quantum mechanics has a world that looks something like this, at the very least. So, on to the introduction. So EQM is basically quantum mechanics without a collapsed postulate and without a hidden variable, but with a costly commitment to many worlds. So I'm interested in a couple questions. One, why is it that not everyone's an Everettian? Because it's such a beautiful solution to the measurement problem. It's a little tongue-in-cheek. If you hang out around Oxford, at least the philosophy department, long enough, you will come to think that EQM is the only way to do quantum mechanics. I think they might teach their undergraduates in this way. Two, how can Everettians learn from the answer to the first question? So here are some critics of EQM. David Albert calls it vulgar. Our children says, quote, "It nevertheless appears that the more extravagant understanding, namely that of many worlds, is one whose basic ontology is clearest, and which provides the logically sharpest solution to the measurement problem." Okay, so he's praising it simultaneously and undercutting it. He's calling it extravagant. Jose Malia and Alex Franklin both cite the extravagance of EQM as a major drawback. Nina Emery says that it's incredibly costly, ontologically speaking. And Norris has condemned it as, quote, "yet another bout of wacky metaphysical extravagance," end quote. So it's not popular with everyone, shockingly. So here's the outline of my talk. First, I will discuss sort of version one of what we call the incredulous stare argument in philosophy, which maybe some of you are familiar with. Basically, if someone gives an argument that seems so ridiculous, you respond to it with an incredulous stare because it's almost not worth a response. And then I will look at a second version of it, which I have dubbed classical divergence. And I've developed this articulation of the incredulous stare, because by articulating what underlies this stare, we can actually more meaningfully engage with it. Then I'll pause and assess the state of play. And in section 4, I'll ask, are these norms justified? And I'll examine them. And based on the subset of norms that I propose that I think are justified, I will provide some possible paths forward to the Everettian, should they wish to improve their ontology. So we'll start with displeasure with excess. Okay, so there's a metaphysical thesis called modal realism, which states essentially that there is a concrete world out there for every maximally consistent set of propositions. And this solicited quite a few incredulous stares, so somewhere this is attributed to David Lewis. I do not know how to refute the incredulous stare. It's not in writing anywhere, but you can take part of his book to sort of reflect this. I couldn't find this quote anywhere, neither could David Wallace, who's one of the leading people who works on EQM, so oh well. But this sentiment is often dropped into various philosophical works. So let's try to understand it so that we can maybe repeat it. Here's this is David Wallace, by the way, and here's how David Wallace deals with this objection in his book. He includes this a series of interludes that consist of little dialogues. And he uses this one to dismiss this objection. So I'll just read it out unless people want to read it out themselves. Sometimes it's fun to act out the script.
You want to act out?
Okay.
Okay, so will you be the skeptic and would you like to be the author?
Sure.
David Wallace? Cool.
Okay. Isn't it still a bit uncomfortable for you that you're arguing that all these other worlds exist, but that there's no possible way to observe one of them?
Not especially. Our best current theory of physics, A, predicts that they exist, and B, explains why we can't normally see them. In any case, we see this sort of thing a lot in science. We can't directly observe a dinosaur, or a quark, or a quasar, or the interior of the sun, but that doesn't stop us taking them seriously.
In most of those cases, it's just happenstance that we can't make the observation. If we were properly situated in space and time, we'd be able to.
Well, if we were properly situated in the multiverse, we'd be able to see the other worlds.
How can you know that?
My best theory of physics tells me so. How do you know that you'd be able to see dinosaurs or quasars if you were appropriately situated?
Okay. So I want to highlight this bit of the exchange. If I were properly situated in the multiverse, we'd be able to see other worlds. Okay, so there are a couple different readings. One, if we were situated in some other world, then we'd be able to see that world, but that seems to me to be trivially true. Two, if we were situated outside of the branching structure, we'd be able to see other worlds, yes, but I'm not sure what sort of observer could possibly occupy that standpoint. So I'm afraid that doesn't especially make sense. So I find myself not, even as someone who's very sympathetic to Everettian quantum mechanics, not particularly convinced by this exchange. Later on, Wallace writes that we don't tend to assume that cosmological theories are a priori more or less likely to be true according to how many galaxies they postulate. So he's starting to construct this version of the incredulous stare argument. And he's pushing it aside, saying that, well, this isn't really a real concern. And in fact, later he calls this like a misreading of the Occam's razor consideration and theory choice. In fact, he says in physics, we never seem to use that sort of consideration. But then John Bell, who's quite a prominent physicist in the 20th century, says this of the Everett theory: this multiplication of universes is extravagant and it serves no real purpose in the theory, and it can simply be dropped without repercussions. This would reduce Everettian quantum mechanics to something that we call Bohmian mechanics. It's another treatment of quantum mechanics that deviates from the sort of classic Copenhagen picture. But Bohmian mechanics is sometimes taken to be a hidden variable theory. So Wallace is not entirely correct, because culturally there are clearly physicists who take this sort of consideration very seriously.
Okay.
Yeah.
A question.
Yeah.
Is the postulation of like multiple worlds in the Everettian theory a purely philosophical assumption, or do they actually have math that talks about it?
Oh yeah.
Or is the math
Great question.
just like the evolution of the wave function?
Yeah, the mathematical representation is just the unitary evolution of the wave function.
Okay.
And then we take that plus the decoherence criterion, which tells us that two elements of, or more elements of a superposition can come out of contact with each other after a certain point. Then the criterion is met, and then they have like sufficiently decohered away from each other such that we can call them worlds. But the theory itself, like the Baire theory, it has been noted in several places, says nothing of worlds. You just have these evolving superpositional states.
Okay, so then I guess my question for this Everettian interpretation is like, yeah, are there physicists who have sort of arguments for why the Everettian interpretation, or like, yeah, is this just a matter of philosophy?
No, there are physicists, particularly cosmologists, who tend to be quite sympathetic to this approach. And actually, I had dinner with a physicist in Merton at an event, and my supervisor and I were sitting there, and we were like, "Oh, so like, what's your preferred version of quantum mechanics?" And he described EQM, but he didn't call it EQM. We were like, "Ah, you're just another Oxford Everettian, my friend." I think that most physicists, like sociologically speaking, will default to saying something Copenhagen-esque because that's what appears in a lot of their textbooks. But then you press them on it and it doesn't really make very much sense at all.
But that phrase, like preferred version, is the idea that like that question's asking what appeals to you, like philosophically, or is it like which do you think
Oh,
is
sure.
true? And
Oh, okay, yeah, good question. So I don't think there may be exceptions, but I don't think very many philosophers even would say that I think this theory is true. Maybe physicists would, because physics education is not very philosophically rich in every case. So sometimes I think you get situations where, like with Hooke's law, like we discussed at lunch, maybe someone thinks like, oh, this is like an element of the book of the world. I've uncovered something like that is a law of reality or something, but I don't think these are just models of reality. And to a first order approximation, all of these different formulations of quantum mechanics that I've described have the same predictions for the outcomes of measurements. So, and they're all equally empirically adequate. Though David Wallace has a paper that argues to the contrary of that EQM makes different predictions from ordinary quantum mechanics. But I've tried to formalize the sort of objection that Wallace is attacking, and I've called it comparative ontic abundance. Ontology is just the study of what there is. I want to make sure I'm not using jargon that is not accessible. Yeah, okay. So for any two theories, TA and TB, that have identical explanatory power and predictive power, we ought to prefer the theory with more modest commitments to unobservable objects. Okay, we can see how this would be a problem to the Everettian, who says that like all of these worlds, once the decoherence criterion has been met, these worlds are inaccessible to us. Okay. Like I said, Wallace is not particularly friendly to this. Instead, he advocates a version of the Occam's razor norm that says instead that we should try to keep the number of postulates and the complexity of our theories as low as possible. We don't really care about the ontology. So this gives us a second one that I call postulate abundance. So for any two theories, TA and TB, that have identical explanatory and predictive power, we ought to prefer the theory with a more economical set of postulates. And maybe this sort of norm is more attractive in the world of mathematics. I would be very curious to hear your impressions.
are there attempts to like formalize what it means to be like economical with like minimize postulates or minimize commitments to unobservable objects? Is there any attempt to be really formal with like applying Occam's razor as ontic?
Oh, sure.
Because this is not as straightforward, right? Because you could have very few postulates that turn out to be rather strong.
Mm-hmm.
And you, in principle, don't know that, right? So how is that measured?
Yeah, good question. I'll start with maybe the ontic abundance norm. This I think is so slippery because we can carve up objects however we want. We could say there's one table here, or we could say there are two tables here, or we could say there are 4 half tables here. Or we could say that all of these objects exist and suddenly we have something like quite bloated, an ontology that's like quite bloated. So that becomes really complicated if we're trying to like count things formally. We sort of have to set a standard for how we'll quantify objects. And in EQM, this becomes even worse because there is no matter of fact as to the number of branches that there are. It's just a function of coarse graining, and we tend to select a coarse graining that is epistemically useful to us. So you could say, well, there's only really one branch. We just have this thing that contains all of these superpositional states, or we could say there are any order of infinity branches. As for the postulate abundance, this is just a loose function of how complicated your postulates are and how many of them there are that you need to specify your theory?
I think it's kind of an interesting question. I'd love to talk about it afterwards, but like as a mathematician, at least my approach is I feel that like both of these viewpoints are incredibly useful and we tend to switch between them. I think we start with postulate abundance and we're like, okay, let's like put in a minimal set of axioms, but then we get nervous if this implies too many things about things.
Yeah.
If it feels too strong. So like sometimes like we use
Okay.
one to lay the foundations, but ontic abundance is how we sort of like touch grass and like check
Yeah.
that we're not getting too. So I think they're actually both.
Okay.
I find ontic abundance more appealing to me. I think, but yeah, I think as a mathematician, I think I see both.
But you need both. Yeah. Yeah. Cool. This is good to know.
I have a question.
Yeah.
Which is, it's not necessarily clear to me that the Borean interpretation has fewer unobservable objects.
Well,
Because when, like, first of all, before the wave function collapse, you're certainly, in the Everettian and the Borean interpretation, the wave function is equally large, right? So it contains equally many unobservable objects.
mhm.
And then, and I would say that the Borean, the Borean interpretation also contains an additional unobservable object, which is like the ontology of what things make the wave function collapse,
Oh, good. Yeah.
right?
Yeah.
Like, why is it that, human observation makes the wave function collapse, but like,
Yeah.
Like what is an observer?
yeah, what is an observer, right? This ontological, so.
Yeah.
Yeah. So I
Yeah.
think like even like setting it up, yeah, if you're sort of setting this up like implicitly so that ontic abundance implies that we should go for like preferring ontic abundance implies that we should go for Borean. Like
Mm.
maybe that's not even clear to me.
You're really an Oxford Everettian. It's happening.
Join us.
Well, yeah, I mean, I think that the point of Everettian is this commitment to multiple worlds, but I would say that like I don't even have that. I just
Yeah, I'm really sympathetic to this framing of things. I do want to say one that we need not be ontologically committed to the wave function in either case. There are people who call themselves wave function realists who say that like the wave function is a complex valued field on some Hilbert space or something. There are other people who say that what the wave function amounts to is like the instantiation of these like mixed states at particular places in space-time. But you can do it a third way and say, well, the wave function tells us it has like predictive power. It's like a tool, but we need not say that it's like something out there in the world. And then as for your critiques of like the Copenhagen interpretation, I'm in full agreement with you. Maybe a better contrast class would be, or element of the contrast class would be called Bohmian mechanics, which basically, because of the hidden variable, has to do with like a determinate position of all particles. It picks out a unique state from the branching structure, and that's essentially Bohmian mechanics.
I see.
Yeah.
But are hidden variable models even mathematically consistent?
As long as they're not. There are two adjectives that if you put in front of hidden variables, they're not mathematically consistent with Bell's theorems.
Okay.
You can remove one of those adjectives. One of them is local, which is speed of light.
Yeah.
And the other one is, I can't remember. The other one's fine.
I see.
We should, sorry, I think we're turning this into a conversation, which is
Yeah.
great, but like, sorry.
Yeah, so if you allow a non-local hidden variable, which would be a violation of relativity, and this makes everyone.
But you need
but
a
it would be-
non-local
yeah.
variable in order to.
Either non-local or the other adjective, which I just can't remember right now.
Yeah,
It's fine. What I'm hearing is,
I'm like reaching back to stuff. that
yeah,
was a
sorry,
long time ago.
Okay, yeah, sorry.
Cool. Okay, so we have these two sets of norms. So another way that, another version of this that Wallace puts forth, involves appealing to, quote, a new principle that we should reject theories according to which the universe exceeds some threshold size. So this is an entirely sort of norm altogether. It has to do with like an absolute criterion. So, I'm going to propose that we also take a look at these absolute criteria where we say, anything with more ontology than this, I think we can rule it out. And same for postulate abundance. If they're either like, if they exceed this degree of complexity, or if we exceed this number of postulates, or it's some sort of combination of the two, then we like ought not admit that theory. Cool. So on the surface, it might look like these absolute criteria are a bit bonkers, and we should dismiss them outright, but I think we have good reason to hang on to them. And this comes down to like two different scales for the application of these norms. So on the left, we have what I'm going to call local. So within a research community, for instance, there was this Many Worlds Interpretation Conference in Tel Aviv in 2022. My proposal was accepted for a poster, but Tel Aviv was quite a long way to travel, so I couldn't quite justify that trip, but I would have liked to go. Anyway, the central question of this is, why isn't everyone an Everettian? And actually, I wish I had had this project active, because I think this could have been very valuable for that crowd. And then in the global sense, we have sort of when minds come together from disparate research communities. So for instance, this Xavier conference on the foundations of quantum mechanics in 1962, where I guess the arguments were fiery. So with the local application, these absolute criteria are really useful on a personal level. They can motivate us to seek a competitor theory that is either like more economical ontically, or more economical in terms of the degree of postulate abundance. The global application, I think, is where these comparative criteria really come into play. And of course, like we said earlier, it's quite a project to actually quantify these things, but I think it's a worthwhile methodology at the very least. But how to weigh these isn't super obvious, and it may just come down to personal preference. I highly doubt that there is a matter of fact out there about how we ought to weigh postulate abundance against ontic abundance. That seems not very plausible to me.
Is there so like with the comparative one, it's sort of like comparative compared to the absolute one in two ways, and I want to check if one of them is just the wording. Like one way in which it's comparative is that, you know, it's you compare two theories, right? And you're saying, whereas the first one just you should reject it, but also you specifically say like we ought to prefer the theory, not that we should reject the other one entirely, just that we should prefer it. Yeah. So like, do you think there's like an even stricter version which is useful, which is like it's somehow absolute in your preference but comparative in your, you see what I mean? Like one where if you took the same thing but replaced prefer with reject the other, yes, that's somehow a different. It sits sort of in between these two, right? Like.
Yeah, I think there's a sense in which outright rejection might not be the move, because you could always workshop that version further. If it has these features that you really, really appreciate, then maybe come back and try to formulate a version of it such that it would win out on the comparative criterion.
Okay, it's interesting, yeah, because I can imagine there being a theory so outlandish that you know, it seems to be perfectly predictive, but you might want to reject it because it's an incredulous stare kind of like thing. So this is nice because it already kind of assumes that like no one's willing to outright reject sort of like the Everettian approach. Like it's a good faith argument. Yeah.
Okay, so here's the final upshot from this section. Even if these norms are justified, the arguments from Parsimony can't really either condemn or vindicate EQM. So I'll take a look at a different version of the incredulous stare that has to do with this problem. Reality, according to EQM, is a bit unexpected. Probably no one goes around thinking, oh, there are all these other worlds. And in fact, our world is constantly splitting into worlds with each process. So again, how do we deal with this surprisingness? Fortunately, me and Emery, who was at Brown for a while, fun fact, but tried to like formalize this in a a different way that diverges away from these ontological extravagance type considerations. And she develops this norm that she calls the minimal divergence norm, which basically says, quote, that we ought to choose the theory that minimizes the difference between the way the theory says the world is and the way the world appears to be. Okay, so we're looking for theories that deviate least from what we call the manifest image, which is a fancy term for the way we perceive the world to be. So maybe some of you are familiar with the idea of Cartesian skepticism. How do I know that there's not an evil demon out there that's deceiving me into thinking this is all reality, but it's actually not? Or am I a mere brain in a vat, something a little more contemporary? Well, we can give Descartes the boot, as it were, because fortunately this sort of norm has helped us out in the past. We don't tend to take these skeptical stances very seriously. I don't personally sit and stress over whether I'm a brain in a vat or I'm in some sort of matrix simulation. Maybe some people do, but it seems like that would prevent us from advancing in our scientific endeavors. So if we accept the minimal divergent norm, this seems to spell trouble for EQM, which doesn't necessarily say that the world is massively different from the way we think it is, but it says there's much more to reality than what the manifest image says there is. But here's a problem that I'll flag. What is the manifest image? How does the world generally appear to you? So surely this varies agent to agent. I'll give you a quick example. So all the way on the left, we have my dad, he's a chemical engineer. And then sort of down the middle, we have my little brother, who's a PhD student in drug discovery and chemistry. They're going to have very different views of what there is to the world, what the world is like. And then my brother, the actor, just over from my dad, massively different views about what the world is like. His manifest image, I'm going to guess, without the quantum mechanics education, is going to look totally different. And then the second from the right had just finished his PhD in astroparticle physics. Massively different ontology. Further, this is theory laden. Like whatever theories we subscribe to are going to shape how we perceive reality. Like, is this a solid table? Is it just empty space? Depending on what I accept about the world, I'm going to think very different things about what there is and what it's like. So this tells me that there's probably no unique manifest image, so this is unfortunately going to be agent relative. And how can we use this to adjudicate between two competitor theories? If it's agent relative, it seems like it could be just as bad as this tension that we found with the parsimony norms. So I did some digging into the history of this idea to help push this project along. And it turned out that Sellers, the person who first proposed it in the 1960s, he says that the manifest image does not include that which involves the postulation of imperceptible entities. It's not meant to be a non-scientific thing either. So here's my pitch. I think we should take the manifest image to be the world according to classical mechanics.
I can't even parse what this sentence is saying grammatically. This conceptual, namely that which involved, does manifest image involve the postulation of imperceptible entities, or I'm totally failing at reading comprehension here.
No, you're totally good. The manifest image explicitly does not include imperceptible entities. It's like the world as it appears to us, it's consisting of tables and chairs and trees and dogs.
Okay.
Is sort of the rough idea. And it's not supposed to be non-scientific. It's a scientific image that sort of bottoms out at what we perceive.
Okay.
Yeah. And I think for the sake of quantum ontology, there are benefits to like formalizing it so it doesn't devolve into something that's agent relative, where one of my little brothers would think this about the world and the other one would think this about the world, and suddenly we're at an impasse. So we look to classical mechanics. Two worries might arise. Maybe you had these worries if you've taken some classical mechanics, but there are unobservable entities in classical mechanics, like point particles and the like, or bits of momentum or something. And then classical mechanics as it stands is contingent.
So what's the meaning of like a point particle being unobservable? Or like I don't quite get.
Oh yeah, it's a point particle is an idealization.
Right, okay.
So yeah, we can't really observe a point particle, properly speaking.
I guess, yeah, why are chairs observable?
Oh yeah, that's the one. Nice.
But
It's
like
right
a
here.
chair is an abstraction, right? Like I can see like something that is black in my field of vision, but the fact that this is a chair
I think this is like
like
evolve into like a Wittgenstein language game, but like we can say the chair is observable because we can all say chair and all believe that we're seeing the same thing, and believe that each other believes that we're saying the same thing, and believe that we all believe that each other like.
that's also true of like point particles or momentum.
I don't think that's true, because I think when you start to look at them a bit more precisely, you can start to be like, wait, where is the point particle?
Well, but like, I have to teach someone what a chair is. I have to teach someone what a point particle is.
And like, is like the existence of point particles really like an axiom in classical mechanics, or is it just like a
Right. Because you could say like, oh, I'm going to only do classical mechanics with solid bodies of finite density,
yeah,
and
or
then say, but I'm using point particle calculations because as an approximation.
yeah, like it's a feature of the model, but not like a statement that classical mechanics,
Yeah.
people make about the world.
Not like essential ontology or something.
Yeah.
I guess in as much as classical mechanics is built on top of Euclidean geometry, it postulates a point as a thing that exists to give like a location of something, right? This says a point exists.
But
Right.
I feel like that is something I can observe, like a point in space.
Really?
Oh, like, yeah, I feel like location is perceivable.
Yeah, I don't know if I can observe it. For me, it's like a spectrum thing of like, yeah, sure, I agree that like boil everything down gets really hard, but like chair, point. I'm just less. It's a relative thing for me, right? Like,
Or maybe a field is a better example. If
Yeah.
you like
Field is right there.
like a gravitational.
or even I suppose like energy, right? It's a
Yeah.
number that is conserved by Noether's theorem, but it doesn't. It's not there.
Yeah, is that observable, or it's like
It depends whose manifest image you're appealing to, because
Yeah.
there were people in that photo who would say that, oh no, it's there.
It's there. Okay, yeah.
Okay. You guys.
But I think that's why the move for classical mechanics might be judicious. Here's an articulation of the problem. Classical mechanics makes use of all sorts of theoretical entities that are unobservable, such as point particles and fields, but that's like decisively not part of the manifest image. So one might think we've gone a step too far in trying to formalize the manifest image, but classical mechanics is a mere idealized representation of the world. And moreover, detecting the real world counterparts to these objects like should be sufficient to solve this worry. We can at least often readily observe the sorts of systems that we use classical mechanics to model, or the consequences of the things that we're using classical mechanics to model. The problem of contingency is this: of all the available theories, why look to proximity of ontology according to classical mechanics as a guide for a metaphysical theory choice? After all, the body of theory that we call classical mechanics is our classical mechanics, is a highly contingent matter. Okay, so there are like many different theories that fall under the umbrella of classical mechanics. We have like even if you looked at the title of the textbook I had, the theoretical mechanics of particles and continua, the theoretical mechanics is different. It's like two bodies of theory. So this might worry you. But here's my reply. The differences between the families of theories that fall within that set and things like EQM or Bohmian mechanics or the Copenhagen interpretation, the differences between these are so negligible that it actually will not matter when we're measuring these distances. I will say that one direction that this might go is I might try to like write a distance function so I can quantify these distances. I'm not exactly sure how to go about it, but I will advertise the work of my supervisor, Sam Fletcher, who has done this sort of thing in different contexts. So I'm really using this to nudge us toward a modest conservatism, because I think it's in our best interest to incrementally make modest modifications to our ontological commitments in order to help us avoid taking on unnecessary onto-commitments that aren't epistemically helpful to us. So I don't think that our onto-commitments will not shift as our scientific theories evolve. I should have said this at the start. The sort of approach that I take to metaphysics involves looking to our best scientific theories and asking, what does this tell us about what there is and what it's like? So of course our onto commitments are going to evolve, but as much as we can be conservative in taking on these new onto commitments, I think we're generally better off. So we ought to employ a sort of conservatism about these matters. So with this in mind, here's my pitch for a new norm that I call comparative classical divergence. So for any two theories, TA and TB, that have identical explanatory power and predictive power, we ought to prefer the theory that minimizes the difference between the way the theory says the world is and the way classical mechanics says the world is. And this, of course, comes in an absolute flavor as well. So here's the updated complete taxonomy of simplicity considerations.
I have some questions, but I don't want to.
Okay.
I don't want to. I think you've got more of your talk, so I need to hear the rest of your talk rather than me asking
Cool.
questions.
Am I okay on time?
We started at like 10 past. You've got like quarter of an hour.
Okay, yeah, no problem.
Okay.
I can definitely, the last couple sections are
We've interrupted you a lot as well. So.
it's totally fine. The statement of the state of play is like quite short, and then I move a little faster for the rest of us. So 1, it's difficult to know how to definitively apply comparative ontic abundance and comparative postulate abundance to either condemn or vindicate many worlds ontologies. And I think this is why there's been sort of a breakdown in communication between people who endorse EQM and their critics. It's not yet clear why we should accept any of these norms. I haven't defended any of them, though I've shown my cards a little bit, I think. So onward, are these norms justified? Oh, and I'll also flag that this is where we're getting into like serious work in progress territory. So first, I will focus on the comparative postulate abundance norm, because many Everettians find this super attractive. So if we compare this to an analogous norm in scientific inquiry, after all, metaphysicians and scientists, their like missions don't seem to be totally different from one another. I don't think they're both concerned with what the world is like, so one might expect them to share methodologies. And I'll flag Nina Emery like argues for this. And in the scientific context, simpler theories tend to stand a stronger chance of confirmation. They're a bit easier to work with. And historically, more complex theories tend to be replaced by simpler theories. So we replaced circular orbits with epicycles with elliptical orbits. It's to Kepler. But unfortunately, there's no real notion of confirmation in metaphysics. So we're kind of out of luck down that line of argumentation. And there's no real notion of progress in metaphysics, which is hard. It's a difficult pill to swallow. And I sat with this for like weeks in despair before I came to accept that this is probably true. Maybe, okay, we develop things relative to particular research programs, definitely, but are we getting closer to the truth? I'm not sure how one would measure that. At least in the empirical sciences, we can look at the world and see our predictions getting better, but we can't really do that with metaphysics because metaphysics has no predictive power. So maybe the sort of simplicity criterion just provides aesthetic benefits. And to be honest, I work on EQM because I think it's really beautiful. So maybe it benefits us to have beautiful theories because then more people want to work on them. But I do think that this norm fails to have any normative punch, and I was really looking for something normative. So let's take a look at ontic abundance, which was your preferred approach. Like before, we have an analogous norm in scientific inquiry. And I think it's generally reasonable to think that some scientific theory A that is identical to some theory B, except for the bonus ontological commitments to entities that play no explanatory role. We should generally prefer the simpler theory. If I had a theory of Newtonian mechanics and then Newtonian mechanics plus something like dark matter that doesn't interact gravitationally, I think it's pretty obvious that we should prefer plain Newtonian mechanics. But again, in the case of metaphysics, there's no relevant notion of confirmation, so I don't think this norm should really apply to metaphysics either. I will flag that like this norm has been used like a lot in the history of metaphysics, but it seems to me, hopefully this is like fine to say, but it seems that we just do it because other people have done it in the past, and that's because somebody in the past decided this was a great norm, and we continue to imitate each other, but there's no like a priori motivation for this sort of norm. But it does capture aesthetic appeal. But like before, this fails to have a normative punch. So on to classical divergence. So like Nina Emery observes, we do tend to prefer metaphysical theses that do not wildly contradict our common sense or our best scientific theories. So we have my friend here contemplating, am I a brain in a vat? You know, we don't tend to take this seriously when we conduct our scientific or metaphysical inquiry. After all, like we wouldn't be able to get off the ground if we were to really get bogged down by questions like this. So Emery has a whole book where she looks at all of these historical episodes and makes this inductive argument that this is a good practice to have. But I think that at best, this account is descriptive rather than normative. And there's no real reason to think that even the norm that I'm trying to push forward, the comparative classical divergence norm, privileges theories that are more likely to be true outright. But I think there are other reasons to adopt this sort of norm. Because I think it can help us organize our research communities more effectively and more effectively explore possibility space. So yeah, like I said before, there's no real sense in which there's global progress in metaphysics, but surely research communities do build on other research from others in their community over time. So I'm going to propose what I'll call a Lakatos-inspired hardcore metaphysics. Lakatos is a 20th century philosopher of science. So here's the hardcore applied to science, or scientific research communities. Basically, the hardcore is immutable, it cannot change. It provides the identity conditions for a particular community. And then there's a protective belt that surrounds the core that involves peripheral commitments that can change and evolve over time. And this account is fabulous. It describes research programs and how they operate, but it also tells us when research programs are degenerating, which is when there are alterations to the hardcore, when people are defecting. And I'd like to appropriate this to create an account of hardcore metaphysics, where research communities within metaphysics can be sort of identified by their hardcores, which are the ontic commitments associated with their predecessor theories. And then as they progress, they try to minimize the difference between the set of ontic commitments of the shared predecessor theory and the new metaphysical theories. And then they can avoid committing themselves to unnecessary ontology that's not actually epistemically helpful. So I'll reiterate, it's not that this sort of norm will help us select theories that are more likely to be capital T true, though some metaphysicians take themselves to be writing the book of the world, as it were, or seeking the book of the world. But I think it will help us more carefully explore possibility space sort of within research programs and make better decisions when we decide which theories to progress with. A concern, this is Karl Popper, and I think this is what he would say, although he hated metaphysics to begin with, but if it were Karl Popper, the metaphysician, I think he would worry that this was too dogmatic and that it would like stifle creativity, but this does not particularly worry me. I think it'll help make us hyper vigilant of the additional commitments that we're taking on so we don't sweep things under the rug, as it were. So I don't share this concern. So what's the Everettian to do? I think there's good reason to think that we've violated some sort of absolute classical divergence norm because the theory is so surprising. So I think it's in our best interest to seek a competitor theory. And just to remind you, this is why EQM of the orthodox EQM is so offensive. It seems to commit us to many worlds where other versions of QM do not. So I think we should see if we can get by with less while retaining sort of the theoretical virtues associated with EQM. And in order to do that, I think it's in the best interest of the Everettian to try to eliminate the worlds from their ontology, for them to think carefully about how we might make do with just one world. But the details of that project are left to a future chapter of my dissertation. Thank you.
Great, thanks. Are there any questions? Yes.
So many questions. It was great. Thank you, first of all. It was a really cool talk. It was great to hear this sort of like this side of the quantum story. It's something I'm super not familiar with. I really like, so what, yeah, with the sort of like ending that you have is another way of phrasing it. I don't know, maybe this isn't exactly the opposite of what you're trying to say, but it sounds like what you're suggesting is that the Everettian approach has been really nice. Your initial thing about it, right, was like it's very postulate light, right? It seeks for this norm, the postulate norm is very good. And now you're sort of saying, okay, we should now do this thing where we now, having used that as a start point, turn to the ontological commitment and try and like address this and sort of bounce back between the two until we land somewhere nicer kind of thing. Is this sort of like a, okay.
Yeah,
That's
yeah,
cool.
yeah. I would really love to come up with some ontology that's more appealing to the general philosopher of physics or the general physicist.
Yeah.
Yeah, bring more people on board so we have more people participating in this epistemic activity.
I just like, I really like the way that you talk about how you talk about this like ontological conservatism of like only making tiny steps towards a thing, and like how you have this core and you focus towards it. And like when you first said this, the part inside of me was like, oh, but this is really bad because you could just be finding essentially like local minima or local maxima when the truth ground reality is like, to get there, you'd have to go over a big bump, which would require a large thing, but then you're going to settle into a much larger well. But then you pointed out this really great thing of like, if you stop being concerned with like the capital T truth, it is true that this is going to carve out better research programs like within themselves kind of thing. So I really like that idea of like, you're addressing this sort of like why conservatism makes sense here, because you're not grounding against the like capital T truth, but building better research programs. So I really like that.
Yeah, thank you. I think this account also has this nice feature where if you become really dissatisfied with the hardcore metaphysics, you can like bounce to a different research program, or you can say, well, this like research community is degenerating and we need to like reassess what our core commitments are. Yeah.
I have just a scientific question really, which is it's unclear to me that that like, yeah, I guess it's unclear to me that these theories really are like predictively the same. Because like, yeah, I don't know, if you consider, or yeah, I guess, yeah, okay, I guess just, okay, I have a question about like, what would the Copenhagen interpretation of the following situation be, where suppose you can build boxes that like perfectly separate things, so nothing ever gets cookie-eared between the boxes. Then we consider like a sequence of like any number of nested boxes.
Yeah.
Each box has like a human in it, and then another box,
Mhm.
right? And then like in the inner box you have a qubit. And then you consider like, okay, the interior human opens the box, like observes the qubit.
Yeah.
And the second, then, but like, so now that has cohered, but because the box is like perfectly decohering, it hasn't cohered with the next outer box, right? So you can consider like any sequence of like opening these boxes and where like for the whatchamacallit, for the Copenhagen interpretation, which box opening would actually like collapse the wave function?
Yeah, that's a great question. It depends on how isolated you want your boxes to be.
They're perfectly
Are they like perfectly isolated?
They're perfectly isolated.
Yeah, good. Okay, so this is a thought experiment called Wigner's friend.
Okay.
In case you want to like
Okay,
go
cool.
poke around later. To be honest, I think there are so many flavors of the Copenhagen interpretation that like the actual historical people who were in the Copenhagen circle would disagree with one another
Okay.
on the response to this. I think it really boils down to whether you want to regard the wave function as like merely tracking what we know about the world, which is probably what Niels Bohr would say, or whether it's something like ontic, where
Like you're saying, like each person has their own wave function.
yeah. So then you could also treat it in this like perspectival way, where exactly
Okay.
on the epistemic approach, each person would have their own wave function,
Okay.
and just because things have collapsed, relative to this box, they're still in a superposition of states. But I think EQM is actually in quite a nice place to deal with something like this.
Yeah.
Because there is no collapse, there's just decoherence.
Right.
So if you have Wigner's friend that you stuck in the box in here, and they've opened their little box with the qubit. From the outside, they're still in the superposition of states. And like from the global perspective, they're still in a superposition of states. It's just the case that decoherence has like occurred within the box. So you have like
Right.
local decoherence that has happened.
Yeah.
Yeah. Is that helpful?
Yeah, that's how, yeah, I don't know, it's just very strange to me that like, I don't know, you can think of experiments like this and the Copenhagen interpretation is like, I don't know. People still believe in it.
My guess would be that like a true Dane would maybe say no, such boxes are already like a premise I'm not willing to accept that could like entirely prevent coherence amongst the boundary. Like you can't put things in a box to that extent. I'm not sure I believe in such boxes. I'm not saying I'm Danish.
Yeah,
I'm just
yeah.
saying I don't believe in these boxes.
But I guess the point is that like any theory should work at the limit. Right.
Yeah.
Like a finite limit, yeah, maybe. I don't want to be an ultra finitist, but like, yeah, I don't know.
Yeah, if your theory, it works for like arbitrarily good boxes, but not perfect boxes. It's like, anyways, whatever.
Yeah, okay, yeah. What I'm hearing is it'd be great if you could make like a BuzzFeed quiz, which tells us at the end what type of QM we are, because I don't know.
Oh man, that would be massively entertaining. Like a personality test.
Yeah, exactly. A personality test that tells you at the end what wave function you are.
You know, what's really interesting to me is I feel like EQM, when I talk to some physicists, they see EQM as like some hocus pocus or something. They're like, this is so silly and so extravagant. Like, I can't believe you would believe this, but Everett himself was like quite a conservative politically. And then this other version, Bohemian mechanics, Bohm was like exiled from the United States because he was a communist.
Oh, that's been great.
And then, yeah, the politics surrounding some of this theory development it's like actually quite interesting.
You did present it like a sort of purely metaphysical like dilemma choosing between these theories, but like, do most people believe that there aren't going to be like observable phenomena that distinguish them, or?
Oh, yeah, I'm glad you asked this. So there's a paper by David Wallace called has something to do with birds in the sky being blue. But I can send it to you after. I have not yet read it, but it's sitting on my desktop, like right here in my fun to read folder. But he argues that there are actual like empirical differences, or the predictive claims are different between EQM and like the rest of everything else. So in principle, it should be testable. I'm not handy with the details of the paper because I haven't read it yet. And I'm not sure what the experiment would look like.
Do you think you would modify your norms? That's really interesting. Like, would you modify so that it's not like, because the assumption, right, was like theory TA and TB have equivalent like predictive and what's the other one power? Like predictive and explanatory power.
Yeah.
And like, what's the balance of like, maybe if theory A has like a little bit less predictive power, but is so much less of an ontological commitment or whatever, like there's a whole new form of relative comparison, right? Where like, in some sense, classical mechanics were like, yeah, it gets it wrong a lot of the time. Like, if you ignore relativity, for example, you're going to get stuff wrong, but like, it's still good enough that like, even when things don't have equivalent predictive and explanatory power, there's still like the norms that you've outlined of like the ontological commitment and the postulate weight are so sometimes like we place more value on them, right? Because so we can actually work with these theories in some sense.
That I feel like that's an empirical question almost. Like what's it feels like that should come down to like pragmatic considerations. What's more useful to the scientist?
In general, I'd be quite like, particularly with the things on the left column, the absolutist sort of criteria. Like, I can't imagine how those things like those thresholds actually like specified and then tested against various theories and practice. Like that seems like and then like, and also it's not really like in general a tool for like distinguishing between two theories, because you could have both theories both pass or fail there. Like it's I just can't imagine how one would actually in practice apply.
It's meant to be like a personal matter. If I like quite like EQM, but I'm like personally offended by the ontological extravagance, then it's in my best interest to seek a competitor theory. And then it's a really like human oriented criterion. I don't think there's any sense in saying like there are more than like this number of things. It will never do.
It just seems like measuring like, you know, the ontological commitments of different theories would be a very like contentious thing in the first place. Like even if you agree on your criterion, then the measurement.
Do you think you could do it in mathematics though? Like, do you think? Because I feel like
I think in some cases you
kind of can, right? Like if I give you like an axiomatization, it's like here are 3 axioms, and then on the other hand, I was like here are 700 axioms. I'm sure in like some formalist sense, you could boil down my 3 axioms into 700 by like, I don't know, doing something, but there's still the like.
Yeah, I mean, for theories, at least you can compare theories by how strong they are, right? In the sense of how many consequences you have.
But there were like things in like that criteria that didn't seem to apply to mathematics. Like there was a distinction, I think, between like, or to me, it seemed like there was a like ontological commitment is about like whether you're committed to believing things about the world. Like the many worlds thing is bad because there's like some physical assumptions you're making as opposed to like a commitment to like the wave function or something, which isn't how this.
I guess I can imagine some people being kind of uneasy about, I guess maybe if you look at like ultra finitists here, they might have similar concerns, right? They were like, oh, my axiomatic commitments have committed me to believe in the number 10 to the 10 to the 10 to the 10 to the 10, and like
people already kind of do a lot of these things without realizing. Like, for example, we already assume that there are uncountably many points for starters, right?
I do think
we never stop thinking, oh yes, we assume that there is a point that is exactly pi centimeters from here and another that is pi squared centimeters from here and so on, right?
Yeah, I do think a lot of this metaphysical stuff you're talking about is interesting in a mathematical context precisely because somehow I think we're half familiar with these arguments, but in another sense, we haven't taken them fully seriously because we're somewhat familiar with them. I think it's very interesting.
Okay, we're about at an hour, so let's thank Ray again.